Partial fraction decomposition. Part 3. Repeated factors. In other words, factors with multiplicity. Welcome to Mark's Math Methods. Watch closely. Example 1. Convert 3x squared plus 2x plus 3 over x cubed plus x squared into the sum of some fractions. Factor the denominator, same as before. When we factor the denominator, x cubed plus x squared becomes x squared times x plus 1. If we do like we've done before, use those factors as the denominators, you'd think it would look like something over x squared plus something over x plus 1. No, not quite. Well, how about this way? Something over x, something over x, something over x plus 1. Still not quite right. We need to combine the two concepts. So we're going to have something over x and something over x squared, and then the something over x plus 1. So that because we have an x squared as the multiplicity in the denominator, we're going to do it as the single and the multiplicity and the double as separate denominators. And then we need to put in placeholders, right? So over the x would go a, over the x squared would go, no. It looks like a quadratic, but it's actually a multiplicity. So it doesn't get a linear numerator. It gets a constant. And then the x plus 1 gets the c. Now we need to find the values just like before. So if we take this one and do like we've done before, clear the fractions. On the left, we just get the numerator, 3x squared plus 2x plus 3. Do the first fraction. One of the x's cancels, so we get a times x plus 1. And the second one, both x's cancel, so we get b times x plus 1. And the last one, the x plus 1's cancel, so it's c times x squared. Now the magic, let's let x equal -1. That eliminates the a and the b, leaving only the c. So plugging in -1 for all the x's gives us c is 4. Now let's let x equal 0. That eliminates the a and the c, leaving only the b. So we plug a 0 in for the x, all of them. And we get b equals 3. Nothing leaves, only the a, so we get to play. Let's let x equal 1. Choose any number you want. I choose easy ones just because it's easier. So 3 times 1 squared plus 2 times 1 plus 3 on the left. On the right is a times 1 plus 1 plus b times 1 plus 1 plus c times 1 squared. So we end up with 8 equals 2a plus 2b plus c. Well, we know the b and the c, so we can plug them in. Plug in the 3 for the b and the 4 for the c. And we end with 8 equals 2a plus 6 plus 4. And a is -1. So we've got a is -1, b is 3, c is 4. Now we can plug those in, and we're all set. So does that different way work for this as well with the multiplicity of factors? Let's find out. So we clear the fraction, we get the same thing we got before. Going to multiply the whole right side out, which gives us 3x squared plus 2x plus 3 on the left. On the right side is ax squared plus ax plus bx plus b plus cx squared. If we look at the x terms, 3x squared plus ax squared plus cx squared, or just 3 equals a plus c. If we look at the x terms, 2x equals ax plus bx, or 2 equals a plus b. And the constant terms yields b equals 3. Oh, that's easy. And we could easily substitute back in, right? We could put the 3 in for the b in the x terms and get the a. Then we could plug the a into the quad squared terms to get the c. But let's see if the matrices work as well. So again, we got 3 equations, 3 unknowns. So for the squared terms, we get a plus c equals 3. For the linear terms, a plus b equals 2. And for the constant term, b equals 3. We do RREF and it yields, oh, those are the same numbers. -1, 3, and 4. So -1 over x plus 3 over x squared plus 4 over x plus 1. Here's another one. Example 2. Let's convert 2x cubed minus 10x squared minus x plus 6 over x to the fourth minus 6x cubed plus 11x squared minus 12x plus 18. And we can convert that into the sum of some fractions. So again, we need to factor the denominator. And we end up with x squared plus 2 and x minus 3, or x minus 3 quantity squared. There's our multiplicity. So we list the x minus 3 and the x minus 3 quantity squared in addition to the x squared plus 2. Again, the x squared plus 2 is quadratic, so it's going to get a linear numerator. X minus 3 is linear, so it's going to get a constant. And x minus 3 quantity squared is still a linear, so it's going to get a constant numerator. Clear the fraction. The left and the first fraction on the right. The second fraction on the right. We get one of the x minus 3's left over. And then on the right is just, the far one is d times x squared plus 2. So we're really only going to have one thing if we use the magic. That's letting x equal 3. And then we're going to have multiple plays. Okay. So let's go ahead and multiply it all out. X cubed. So the 2x cubed has to equal the ax cubed plus the cx cubed. Or 2 equals a plus c. For the x squared terms, we get negative 10x squared equals the negative 6ax squared, the plus bx squared, the minus 3cx squared, plus the dx squared. Or negative 10 is negative 6a plus b minus 3c plus d. For our linear terms, we get negative x equals 9ax minus 6bx plus 2cx, or negative 1 is 9a minus 6b plus 2c. And then, of course, our constant is 6 equals 9b minus 6c plus 2d. So now we have our 4 equations and 4 unknowns. So here are our 4 equations. Go into 4 equations, 4 unknowns in your matrices. And I always put x cubed on top, x squared, x, and then the constant. It doesn't really matter the order in which you write them. I do that so I'm consistent. It helps me not get lost. So for the x cubed was 1a plus 1c is 2. For the x squared was negative 6a plus 1b minus 3c plus 1d equals negative 10. For the x was 9a minus 6b plus 2c equals negative 1. And the constant was 9b minus 6c plus 2d equals 6. You run the RREF, and you end up with A is 1, B is 2, C is 1, and D is negative 3. So there we have it. Much easier to integrate in the individual pieces. I hope the presentation was helpful. Thumbs up, subscribe, comment. And if you have any problem types you'd like me to demonstrate, there's my address.